So for those of you who don't know me, which is probably most of you, I work with Serena De Beer at the Max Planck Institute here in Mulheim. And so a lot of what we do is focused around not just X-ray absorption spectroscopy, but combining lots of different kinds of spectroscopy with X-ray and also with theory to understand chemical problems, particularly in bioinorganic chemistry. And the real focus of our institute comes from our need globally to satisfy energy demands. So I think this is a need slide just to justify where we're coming from. If we really want to expand our use of things like solar, hydropower, and wind power, which suffer from temporal variability and things like that, we need to develop a lot of different ways to actually provide this energy quickly from long-term and short-term energy storage solutions. And of those that are currently in practice in the power grid, really the hydrogen fuel cell is the only thing that's commonly used chemically. And that's something that we'd like to see change, because we believe storage of chemical energy in a chemical form is really the way of the future. And hence the name of the institute, the MPI for chemical energy conversion. And the reactions that we really focus on here are both hydrogen production, but also a number of other critical reactions, both for production of fuels and for other important processes that we have industrial, like ammonia production, which takes 2% of global energy as we know it, ethanol production, oxygen activation, and so on. And as bioinorganic chemists, it's particularly interesting for us that all these reactions can be performed or are performed in nature by different sorts of enzymes in all sorts of bacterial organisms, or in plants, for example, for photosystem too. And so what's also important for us as bioinorganic chemists is that these utilize 3D transition metals. And so to understand how the secondary coordination sphere environment and the identity of these metals affect their ability to catalyze the reactions, we like to take this approach of theory, spectroscopy, and also model complexes to develop an understanding of how these enzymes function. And using that, try to figure out how we can actually make better catalysts to use industrially. So today, of course, as you saw from my title, I'm going to focus on nitrogenases, particularly molybdenum nitrogenase. So molybdenum nitrogenase is a two-component protein system, and it consists of the catalytic MOFI protein and a reducing iron protein. And when iron protein binds to MOFI, it can transfer a single electron, and through subsequent binding on-off events, it transfers a total of 8 electrons to MOFI, which then catalyzes the reduction of nitrogen to 2 molecules of ammonia. And I keep harping on why it's interesting for bioinorganic chemists, and it's because it uses a pile of different metals. This includes a 4-iron 4-sulfur cluster for electron transfer of the iron protein, a fused double cubane P cluster, which is also serves as electron transfer in the MOFI protein. And lastly, arguably one of the most, if not the most complex catalytic cofactor known in nature, the FMOCO cluster, which has 7 irons, molybdenum, and a central carbide. So this has been very heavily studied for quite some time, but there's still a lot left to be figured out about it. And particularly this is with regards to intermediates of its catalytic cycle. So as I mentioned before, iron protein binds, transfers a single electron, it grabs a proton from water through another proton chain, which is not well described yet, and you take one step forward in this catalytic cycle, going from E0 to E1. If we do this again, we get to the next step, E2, and at this state, since we've accumulated 2 electrons and 2 protons, we can of course produce hydrogen as a side product and relax back to E0. But if we pump in electrons and protons fast enough, then we can move up to E3 and E4. And of course, all of these can produce hydrogen as side products, relaxing back in the cycle. But at E4, something important happens where we can actually bind nitrogen. This happens through reductive elimination of hydrogen to form an N2 bound state, and through 4 electron, 4 proton transfers, subsequently produce 2 molecules of ammonia. And so this is the kinetic model for how it works, but exactly the nature of all these different states is not very well known. And this is in part because it's extremely difficult to control and actually isolate these different intermediates, particularly building up to E4 and after the E4 state. This is because, as I mentioned before, this iron protein is coming on and off, transferring single electrons, and that really controls how fast you move from E0 to E1 to E2 to E3. And these all happen at effectively the same rate. Meanwhile, because we're not dependent on the iron protein at all for relaxing back, and the chemical nature of these different intermediates is also different, the relaxation between these states all happens at different rates. And so if you want to try to populate one state more than another, you have to play around with your KF, or how fast you're pushing electrons into the system, and balance that with the back reactions. And if we want to look at E1, which is arguably the simplest one to do, we just have to balance our rate of electrons going in with this K-1, or hydrogen production from E2. And by using a specific ratio or a carefully adjusted ratio of the iron protein to molybdenum, we can selectively populate only the E0 and E1 states. And what we want to ask first in this most simple step of the reaction cycle, which is still very poorly characterized, is what is the nature of the E1 state? Namely, where does the electron go? Does it go to molybdenum or does it go to iron? So it sounds like a pretty simple question, right? And at a second step, we also want to ask the question, where does the proton go? Do we have something like formation of an iron hydride, or do we have protonation of a sulfur on this cluster? So we're interested in both where they go and very specifically where they go on the cluster itself. Of course, we're not the only people to look at E1, but we're one of very few. So there's only two previous studies on the E1 state, one from 1995 with Steve Kramer, who I'm sure most of you are familiar. And when they performed EXAFS on this, they found that we had unusual contractions of the average bond distances that were fit for molybdenum, and also contraction of the average iron-iron distance. This seems kind of counterintuitive when you'd have a reductive process. Normally bonds tend to expand as you reduce transition metals. Also, it's interesting how large the differences in bond distances are here. So this is something that we felt would be worth reinvestigating. Also, in part because unfortunately the E0 that was used was varied per path, and so the fitting procedure wasn't really physical here, and so it's very hard to trust those changes in bond distances. The second study that was performed is almost completely iron 57 Moss power, and so as this is an X-ray oriented talk, I'm not going to dive into Moss power spectroscopy, but if you'll believe me, I'll say the parameter delta is an indicator of average iron oxidation state. And so in this study by Eckert Munk and coworkers back in 2000, they looked at what happened when you went from oxidized FMOCO to resting FMOCO to turnover FMOCO, something that was oriented towards E1 in terms of the experimental conditions. And then they also looked at what happened when you cryoreduced. Now, cryoreduction occurs at 77 K and is typically performed using a cobalt-66 source, although for this study, they used a synchrotron source for cryoreduction. And what they found was that there's a shift of about 0.6 or 0.06 millimeters per second, which, if you believe me, about translates to about a single oxidation state change on average over the bulk of iron in FMOCO. And when they looked at the native turnover system, this was a much smaller shift. In cryoreduction, they had a very similar shift, and from that, they concluded that when you cryoreduce your sample, it looks like you have an iron-centered reduction, and when you put it under native turnover, it does not look like an iron-centered reduction. And so as a negative result, it was proposed that molybdenum was the center for reduction. And this didn't seem exceptionally unusual because at this time, molybdenum in FMOCO was believed to be molybdenum 4. And actually the De Beer group since then has demonstrated very well that molybdenum in FMOCO is molybdenum 3. And it's a very unusual molybdenum 3 with a non-Hund electronic configuration, but molybdenum 3 nonetheless. And so going from molybdenum 3 to molybdenum 2 would be extremely unique, to say the least. So this is all worth reinvestigating. Now, if we look at their conclusions, right, this was all based on the assumption for the Mossbauer that we have a 1 electron difference. But when we go from E0 to E1, we don't just add an electron, but we also add a proton. And so maybe the difference between generating our actual E1 state and generating this cryo-reduced state that they observed is not a true difference in the location of reduction, but is actually just a difference in whether or not the cluster has been protonated. And you could solve this problem by annealing at certain temperatures that would allow proton mobility. And in theory, you could generate E1 then from this cryo-reduced state. So this is a hypothesis that we wanted to test as part 1 of this talk. And so we generate a series of samples, both resting, turnover, and several different conditions of cryoreduction, as well as annealed cryoreduced samples. And then, I forgot to mention, so 30 kilogray is an amazingly large amount of radiation. It is very difficult to reduce this protein. And for example, 0.01 kilogray is 100% lethal dose in humans. So just a perspective that these do not damage very easily under irradiation. Then we planned to use a whole series of characterization techniques, namely EPR is really good for quantifying states. And with that quantification using being able to better analyze our X-ray absorption and Mossbauer spectrum. And then we also, at the end of this talk a bit about QMMM modeling as well. And so I don't know if there's any questions really quick. This is a decent time for the preliminary intro. I don't know, or I can keep going. What do you think, Jacinto?
I would keep going. I mean, nobody wrote anything, so.
All right. So of course, I'm giving a talk to a series of X-ray experts, but I like to keep a little bit of a simple pedagogical component to my talks. And so I thought it would still be worthwhile to have this. In X-ray absorption spectroscopy, as most of you know, we basically irradiate an absorber of interest with X-ray radiation. And at a certain point, as we move up in energy, here we can start exciting from core orbitals to our valence orbitals. Depending on the nature of our sample, we could have pre-edge features or other edge features. And as we continue to increase that energy, we have absorption and excitation to higher and higher energy bound states until we hit a certain point at which the kinetic energy of the electron can break free from the potential of the nucleus, and it goes out into space and propagates out as a photoelectron. Now, when we encounter surrounding atoms, it could either pass through or it could scatter off of those surrounding atoms. And this scattering can occur in either constructive or a destructive fashion. And depending on the nature of the scattering, which is also energy dependent, it changes the probability of this photoelectron to be reabsorbed by the original absorber. And as a result, we get our nice sinusoidal pattern, which is known as our EXAFS region. And from this, we can actually analyze and fit this data by transforming into a K-space, and by further Fourier transform, we can get out structural information about our system. Both the identity, roughly, and the distance of these scatterers. Now, this is important for later in the talk, but it seems really simple now. There's two predominant ways that most of us, or from a practical standpoint, go about recording hard X-ray spectrum. The classic way is transmission, which follows the Lambert-Beer law, and it's very effective when your absorber is very concentrated and absorbs a lot of radiation compared to your scatterer. On the other hand, fluorescence tends to be a lot more advantageous technique when scattering is a major factor and your absorber is at very low concentrations. In this case, we have some sort of detector or analyzer which collects photons over a given solid angle theta, and our signal is proportional to this fluorescence yield over I0. Of course, because we're looking at fluorescent electrons, or fluorescent photons, there's a lot of different options and flavors for fluorescence spectroscopy, looking at relaxations from all these different kinds of sublevels, as well as Auger electrons. We can do this either, most simple way is total fluorescence yield, where we observe all fluorescent photons. effectively we go over our entire range of emission. We could also do partial fluorescence yield, where we use solid state detectors that are capable of discriminating energy over a relatively wide gap, but it still can narrow things down to, say, the K alpha lines. And last and most precise is HERFD, or high energy resolution fluorescence yield spectroscopy. And here we use an actual emission spectrometer, which involves a detector, a sample, and analyzer crystal on a Rowland circle to selectively choose only photons of a given energy. And therefore we can detect for that given energy how it varies as a function of incident radiation. And out of that, we can get our HERFD absorption spectrum. And so since we're using an emission spectrometer, we tend to need a lot more flux because we're throwing away a lot of photons. We have a lower effective solid angle. But with this really small spot size and intense flux, we can get an experimental resolution that approaches the core whole lifetime broadening of the system that you're looking at. And out of this, we get a line sharpening effect, which is really advantageous and why it's actually called HERFD at the end. With HERFD, we could also choose other lines, for example, in the K beta 1,3 or K beta prime, or even in the valenced core region, to get other selective chemical information and look at the absorption spectrum as a function of more specific processes. So it's actually really overall a very powerful technique in XAS. And just as an example of this line sharpening effect, we can see for iron K-edge that we have two pre-edge features that come out of an otherwise very broad single pre-edge feature from the partial fluorescence yield. And even more powerfully in the molybdenum K-edge spectra, we go from something that looks kind of like a broad sinusoidal absorption spectrum to something with a distinct pre-edge feature, rising edge feature, and a white line feature. So this really can give us a lot more information about the system, particularly at molybdenum, than we can get out of partial or total fluorescence yield experiments. And so with that, let's go back to the question of where the electron goes, now that we have a little bit of background of how at least I'm thinking about these experiments. If we want to ask what happens at molybdenum when we have reduction, usually it's good to have a couple model complexes to demonstrate what might happen. If we look at going from molybdenum 4 to molybdenum 3, we have a diagnostic 1 electron shift in the edge. And that's really our biggest indicator for reduction at molybdenum. And since we only have one unique molybdenum and nitrogenase, we would expect to have something of a similar magnitude if we have a 1 electron reduction in the FMOCA cluster. And what we see is absolutely nothing. So this is I think these are very pretty spectra. They're collected over quite a long time, and we don't observe any significant changes. So this seems to indicate pretty strongly that, counter to what was proposed in this 2000 Mossbauer paper, we really do not have any observable reduction at molybdenum. With that in mind, of course, then we have to have reduction at iron, right? So let's look at what we think would happen based on model complexes to iron. If we take a molybdenum iron cubane, for example, this is really popular, what our group likes to use as a standard. These irons are very delocalized mixed valent, and in this case we have a diagnostic shift in the edge of about 0.6 eV or so, 0.3. And if we look at the different spectra, we can see this results in about 15% difference total at the edge, 12 to 15. If we look at a different system, though, that's not delocalized mixed valent, but localized mixed valent, we can also see much more interesting changes. So instead of just a shift in the edge, which we observe in going from diiron 3 or a diferric to the ferrous-ferric dimer, when we go from ferrous-ferric to diferrous, we do not have any observable shift in the edge, but instead a decrease in pre-edge intensity, a decrease in rising edge intensity, and an increase in the white line intensity here. So this is what we're going to use as our fingerprint to see what might happen from iron's perspective. Now, if we look at MOFI, now, big moment. Oh, there's almost nothing. Like, what's going on? So it doesn't look like anything's changing at molybdenum, and it doesn't really look like anything's changing at iron. except if we look really, really close, there's a small change in the white line that we can observe, but this is tiny. It's kind of laughable, right? If we look at this different spectrum, we see a general increase in intensity across most of the edge, but this is, you know, 0.5%, like, you know, 0.7% or so. And so the question is now, is this what we'd expect? So if we look at the amount of difference that we're seeing from either the cubane or from this dimer, it's on the range of like 10 to 15 and about 5%. And so if we calculate back and you consider that we actually have 15 total iron in MOFI, then what we're observing is not that ridiculous. 0.5 to 1.5%. Yeah, we're more on the 0.5% side, but it's not unexpected. The question then is, are these changes significant at all? And so this brings up the question of how do you determine, or what's a good way of determining significance in at a K-edge X-ray absorption spectrum. So if we remember how we actually do this experiment, as most of you know, we usually pick a point on a sample, we irradiate it, we do damage studies, see how long you can irradiate it before shifting or changing the chemical nature of your system. And then we set something below that as our total scan time, and we collect a spectrum. Then we move to another spot and we collect a spectrum, and we keep on going over the sample, collecting spectra until we're happy with our signal and noise ratio, or that it looks clean enough effectively. Now, since we have a scan population though, that means that we can actually use the individual scans to go ahead and calculate our deviation. All we have to do is define chi of I as our ith scan, and then calculate the average spectrum. And from this, you can really easily get out your standard deviation of your spectrum. So if we take this definition and bring it back to our K alpha HERFD XAS, we find that no, none of these are remotely, are even remotely significant. And so this is really a flaw of, this is one of the very few flaws I find with HERFD, is that you have relatively fast scanning times. And so intrinsically you end up at a state where you'll kind of level off in terms of how good your signal to noise ratio can get. So the question then becomes, if we want to look at the system and answer these questions using X-ray absorption spectroscopy, we need to reduce those error bars. And in that case, really what we need to do is reduce the level of stochastic noise in our experiment. And so in the HERFD experiment, as I mentioned, we have relatively short times with more intense beam, because we have to have more intense beam to get enough counts to do fluorescence yield, or to do fluorescence measurements. And we have a relatively, not tiny, but kind of a medium spot size here. And so what we found in these samples, that we could have a scan for about 90 seconds, which is really pretty stable. But even with 300 scans, getting about 400 counts per scan, you know, we didn't see a significant enough, we don't have significant enough changes. Now, if we increase our scan time, we can reduce that stochastic noise. On the other hand, increasing the scan time means that we really would have problems with damage. And so if we want to reduce problems with damage, we need to spread those photons out over a larger spot. And not ideally, but a lower flux can also help reduce damage. Another big part of this is increasing the solid angle. So the solid angle you can get by closely bringing in a germanium multi-channel detector will be a lot larger than, or a bit larger than what we can get ideally out of an X-ray emission spectrometer. And so with comparable total collection times, but much slower for the partial fluorescence yield, I'm getting about a little bit over 3 times as many counts total for a spectra, or total for the final spectrum. So with that in mind, we can go back, repeat these experiments using partial fluorescence yield. Now we don't have as beautifully resolved spectra, but we actually have significant difference in the results. And this is really huge for this kind of very detailed experiment with a lot of unique centers present. And chemically, we see something that looks a lot like this localized mixed valent dimer. So we have a decrease in pre-edge intensity, a decrease in the rising edge, and an increase in white line intensity. The fingerprint, which looks a lot like this black line here. What's more is that when we compare our cryo-reduced sample in black with the cryo-reduced annealed sample, the cryo-reduced annealed sample seems to be gravitating towards our E1 state. And I can also mention here that some of the differences we're seeing is because when we do the cryo-reduction, we also generate a very small amount of oxidized P cluster, and that can account for basically the differences that we're seeing here. But that's another story or another one for questions. So it looks like we have something that is an iron-centered reduction, and not just iron-centered reduction, but something relatively localized to an iron-3 center. Now, we took a step back and said, does this work out with the mouse power? And so we gave Eckhard Muenke a call, and he actually still had one of the original samples from this 2000 study. And these are really tricky to get because they've been selectively enriched only at the FMOCO Center, and the experimental side of making those is an absolute nightmare. But we took that sample and we cryo-reduced it, and we have a similar shift to what they observed before. And importantly, if you anneal the sample, that shift goes down and it matches that of E1. So now this really supports, together with the XAS, that we do not have molybdenum-centered reduction. We have an iron-centered reduction. It looks relatively localized, and that our hypothesis that the connection between this cryo-reduced state and the E1 state seems to be the availability of a hydrogen. And so the next step here, maybe I'll pause for questions, is where does the proton go?
Yes, we have several questions. Yang Ha suggests, when you assign the molybdenum oxidation, is molybdenum electronic structure localized on itself or delocalized with iron?
We have very strong coupling between molybdenum and iron, and this is based on DFT calculations by Ragnar Bjornsson, and it also matches what we've observed for cubanes. So we've done some XMCD on here to look at the local electronic structure at molybdenum, and at least in molybdenum cubanes, it looks like a spin 1/2 system with a non-hooded electronic configuration. And this can only come about from a very unique interaction with the 3 surrounding irons. So it is strongly coupled with those.
And Yulia asked about what was the temperature that you did.
Sorry, can I ask myself, because I have several questions and lack of details made it difficult for me to follow. So first of all, this X-ray induced damage experiments, what was the temperature?
About 10 to 15 K.
And did you try, other temperature?
Well, are you asking about when we were doing HERFD measurements, or in terms of determining our total scan time, or are you talking about the irradiation experiments?
It doesn't matter, because what I feel is, you just have not been damaging it at optimal conditions.
Are you asking about, again, the generation of the cryo-reduced samples? Or are you asking about the cryo-reduced samples were not prepared as synchrotron? They were prepared using at 77 Kelvin using 66 cobalt source.
Okay. So that helps. So the second question is this E1, which you compare with cryo-reduced, how that one was produced?
So E1 is produced by putting in our turnover with a very, very small amount of iron protein present. And it reaches a steady state where you have a significant, so we do this by EPR for quantification. So the E0 state is EPR active, E1 is EPR silent, and E2 is EPR active. So you can actually track and see your sample composition for E0 and E2, and whatever is not E0 or E2 should be E1.
Okay, and do you know what is the percentage?
It's about 50%.
Okay.
So all of the spectra I've shown you have been corrected for that E0 contribution.
So last quick question. So do you know this first step, E0 to E1? Is it proton-coupled electron transfer? Do you know characteristics, pH dependence of this?
We're working on that.
Okay, thank you.
Yes, that's whether or not so it has never been observed separately. I'll put it that way. We've never observed it's never been observed separately at regular conditions of the protein, so like 7.3 pH. You can protonate the cluster separately at low pH, like below like pH, around pH 5.5, I think. You can get this E0H plus state. Yes. So then the question of whether it's truly a PCET or not is, yeah, needs a lot more investigation.
Then Jerry has a couple of questions I will read because he cannot say. So the first one, of course, it will be the resolution. So how much energy resolution do you really need to get sharpening of the features of the HERFD? There are higher solid angle options at 2 to 4 EV. Then there are at 0.5 to 1 EV resolution.
Yeah, so the game here is, for us, we wanted the HERFD particularly for molybdenum, because looking for those changes in oxidation state at molybdenum from partial fluorescence yield, you're going to see just these subtle shifts around. You might get it if you have a real shift in the edge, but HERFD is really critical for that. From the iron perspective, it's nice, but it's not as critical. So this is why we also chose to go with the partial fluorescence yield experiments for solving that problem.
And then the other one is, now that you know the energy range where there are Zanus difference, could you reduce the energy range of the HERFD scan to emphasize, for example, on the pre-edge feature?
So in the HERFD scan, you still need to be able to normalize your spectrum.
Mm-hmm.
So in our HERFD scans, we're already Zanus focused. Completely Zanus focused, and I don't think we can we were doing these at ID26, and if somebody there could correct me, I don't believe we can do well, you can do regional scans, but it would be really strange to try to put together a regional scan where you're cutting partway at the edge.
Mm-hmm.
I would think you'd have some normalization problems with that. But I will emphasize that 90 seconds scan time is for ID26, and the samples are group runs. That's a really long time. It's a very, very stable protein. At molybdenum, it's stable for 5 minutes in the beam. If you compare it to a lot of other systems that are a lot more sensitive, like high valent iron, where if you're lucky, high valent iron or manganese, where you get maybe like 2 seconds or less for an entire scan. Then we're actually very lucky to be working with a system that's so robust, which is kind of expected because it is really hard to reduce the thing, both in vitro, in vivo, and even by irradiation. So even with all those advantages, with HERFD, we couldn't get that far enough out. And I'll note again, one of the reasons that those errors look particularly large is because you have to remember we have to propagate our error through the spectrum. So it's not just the error in an individual spectrum, but once you take the E0 component out, that multiplies your error. And then once you do the different spectrum, that multiplies your error again. So
then there is just a small question from Yama. Are there any existing model complexes that have any reactivity?
For nitrogen?
I assume, yeah.
Yes, there are model complexes out there with low turnover numbers. Both, if you're interested in these, Pat Holland, Jonas Peters, for the iron chemistry, those are two of the big guys there. Of course, Schrock, Nishibayashi, these guys also do a lot of work from the molybdenum standpoint. So because back in the 80s, when people were looking at reactivity of nitrogenases, and they didn't know the structure, but they found there's molybdenum in there. They're like, oh, this molybdenum really has to be in there for a really good reason. It probably, they assumed that was the source of, or the active site for catalysis. And since then, we found this is very, very unlikely, but it still inspired an entire range of really colorful model chemistry. That's,
I mean,
extremely respectable in its own right.
It's funny because actually I gave a talk here in the Royal Society with Ingram, and she was talking a little bit about the molybdenum still being there as a part of evolution, you know. That,
yeah.
As the oxygenation of the atmosphere happened, more and more enzymes starts flushing out molybdenum, and maybe in some of them, the molybdenum is kind of a lingering evolution that is still has to take place. Might not be so essential for the entire reactivity.
I will say there's 3 nitrogenases that are known. They are very, very similar. And there's molybdenum nitrogenase, there's vanadium nitrogenase, and there's an all iron nitrogenase. And those vary completely by what is here. Although the crystal structure of the iron nitrogenase isn't known, and a belt sulfide is replaced by a carbonated vanadium nitrogenase. But they're assumed to be otherwise very, very similar clusters. But the molybdenum nitrogenase is, by expression in organisms, is always preferred. So all organisms that fix nitrogen express molybdenum nitrogenase. Some, when they can't get enough molybdenum, can also produce vanadium nitrogenase or iron nitrogenase, or maybe both of those, depending on what they can get, but it totally depends on the organism. And in terms of efficiency, this back reaction of hydrogen production seems to be much higher in vanadium and iron nitrogenase. So vanadium nitrogenase is less electron efficient than molybdenum nitrogenase, and iron nitrogenase is even poor. Recent studies have shown that the limiting stoichiometry is the same for all 3 enzymes, but they're just not as effective at binding nitrogen before releasing hydrogen. So it does seem like molybdenum is doing something important there. But of course, that also has an impact from what the secondary, it's also impacted by the secondary coordination sphere very heavily.
Yeah, good. So
go on.
Please continue so we get to the end of your time.
So great. So the second part is a little bit quicker than the first. Good for us. In the second part, what we're going to do is, since we already looked at the Zanes, we're now going to look at EXAFS. And what we really want to do with the EXAFS is not only reaffirm or corroborate what we have observed already, but provide a very tangible point to kick off a QMMM study. And since most of you are familiar with EXAFS, I will just jump into scattering paths right away. Since we have crystal structures of molybdenum nitrogenase, we're actually very, very, we're very lucky in that respect, where we don't have to guess at the exact coordination numbers and the exact pathways that could be present, because we can already look at the crystal structure to get all of these out. And so from the molybdenum standpoint, it's really simple. We have oxygen, nitrogen as relatively light atom scatterers. We have molybdenum sulfur, and we have molybdenum iron. Depending on your resolution and what you believe from the crystal structure, maybe you can differentiate the oxygen and nitrogen, but I'll touch on that later. From the iron side, it's a lot more complicated though, because again, we have 15 unique iron here. And so in FMOCO, there's iron molybdenum and iron sulfur, at least one short iron-iron distance, a long iron-iron distance, and possibly the iron carbide, although we found you really, because it's so light, you really can't reasonably fit it. In the P cluster, it's a little bit simpler, but you still have iron sulfur and 2 different total iron-iron distances that you have to deal with. And so the real question here, quick, is how we can actually compact and do some reduction in terms of our parameters and appropriately fit these without overfitting them. If we look at the crystal structure, we can actually just plot some histograms of the average bond distances. And so molybdenum, the iron sulfur distance in the FMOCO cofactor is pretty tight. It's all within about 0.15 angstroms, and obviously deserves only one scattering path. The P cluster is a lot more disorganized in this sense, but most of the iron sulfur scatters are still in this range of like 2.25 to 2.4 or so angstroms. And so we're still going to only use one scattering path, because the contributions from these guys are not going to be too large and don't really deserve a separate scattering path alone. This is a similar story, and everything FMOCO versus P cluster like. So if we look at our long iron-iron distances, FMOCO has very well conserved long iron-iron distances that come from the scattering between irons across each other on the cofactor. And if we look at the P cluster, there are also a number of long iron-iron scatterers, but they're really, really spread apart in terms of total distance. And so most of what we can fit is only going to be this tight bundle here. And it'll have a small amount maybe of P cluster contribution, but it's a pretty strong indicator of what's going on at the FMOCO cluster. And lastly, for the short iron-iron distances, again, for FMOCO, these are pretty tightly conserved within about a range of 0.1 angstroms, and the P cluster is much more spread apart, but it's not so spread apart and not so skewed as in the iron-sulfur distances. And so here we're actually going to split these into two shells. One that's going to involve FMOCO and the shorter P cluster iron-iron distances, and one that has the slightly longer P cluster only iron-iron distances. So we have single iron-sulfur, and iron-iron long and two short iron-iron scattering pathways we're going to invoke here. If we go back to molybdenum really quick and fit these scattering paths, I want to mention that we're actually measuring the E0 sample and this mixture of E0 and E1 as Yulia pointed to earlier. And so when I'm talking about this E1 spectrum, it's actually been derived from the other two by subtraction. Now, with that in mind, it means that I have actually two data points I can fit to see if I have any trends and changes in distances. And it's important that whatever I find from my derived E1 spectrum is also supported by the E0 plus E1. And so if I look at the distances that I fit for molybdenum, we find that really nothing changes. This is what we would have expected since we don't have a change in oxidation state. And importantly, in this two-point fitting process, I find that even though it looks like on either side, maybe something small and significant is happening from the molybdenum iron standpoint, they contradict one another, and it supports that really we don't have any effective change in distance. From the iron side, as I talked about before, we also have our iron molybdenum ion path that we've added into this, but we do have significant distances, and those do trend a little bit. And importantly, our iron sulfur distance seems like it increases. Our short iron-iron distance, which is this mixture of FMOCO and P cluster, changes a little bit, and so does our long iron-iron. And so just as a reminder, the long iron-iron is a really good indicator of what's going on for FMOCO, and a little bit less so for the short iron-iron, but still reasonably. We also see that for the second short iron-iron distance that we really have no effective change, which at the P cluster, we don't have any change in oxidation state. It stays a constant all ferrous state. It cycles through one electron oxidized in an all ferrous state, but the population that we actually see is the all ferrous. So this is interesting in its own respect. We can compare that to model complexes for crystal structures, a whole wide range of them. And we find that this increase in iron sulfur distance with a decrease in iron-iron distance is pretty diagnostic for single electron changes in iron sulfur clusters, as well as in the iron protein itself. So now, as I mentioned before, what we really want to do with these differences is use them as a jumping off point for QMMM investigations. So for those a little bit less familiar, in QMMM, we basically have a very large region or large system that we treat with molecular mechanics, and then a more isolated or specific system that we would like to more precisely understand, and that we will treat here with DFT using TPSSH as a functional. And specifically, our QM region is not only the FMOCO cluster, but also important surrounding secondary coordination sphere residues that can alter things like its favorability to be protonated and also the electronic structure itself. So these are really important to include in the calculation. Now, once we have our QMMM space decided, we can actually look at different models of what E1 might look like. So we go through all the different possibilities of the broken symmetry states between these iron centers when we add a single electron. And then we also look at different protonation sites for both the belt sulfide clusters, either subcubane. We also look at whether we have hydride formation, whether you can protonate the central carbide as Per Ziegbahn is a big fan of that one. And we also look at protonation state of, importantly, this neighboring histidine residue, 195, and on the homocitrate, which I haven't included here. And we take all these models and we boil down all of the structural parameters and compare those changes in structural parameters between the calculated E0 and E1 state with those experimentally observed. And we can get this bulk RMSD. Now, I will say that it blankets some kind of harsh violations by a couple of models, particularly when we don't have a proton present and the S3B. There are some distances that change a lot in those that we would have seen in our EXAFS, but nonetheless, our S2B and S5A positions seem to have the best RMSD, and it also seems to favor this N epsilon protonation state of the histidine. If we also look at the actual energy profiles, what are more favorable models relative to one another, we also see the S2B and the S5A are significantly more favorable than basically anything else that we tried out here. And so between this decent match with our experimental data and this energetic data, it seems like it's a really good indicator that one of these sites is responsible for, or is the site of protonation in E1. Now, what's interesting about this is that we also get an idea of what's happening at the site of reduction. And in all of these calculations, we find that the most favorable site for reduction is always on the molybdenum subcubane, and it is always on the iron that neighbors this the protonated sulfide. And so for S2B, this would be reduction of iron 6, and for S5A, that would be a reduction of iron 7. And so from all of this together, we have a really precise proposal for what the E1 state looks like. So we do not have molybdenum-centered reduction, we have an iron-centered reduction. We have protonation of a belt sulfide, not another sulfide on the cubane or of central carbide, for example, or formation of a hard hydride. And we have a very good idea of where reduction is actually occurring, that it's most likely on this molybdenum subcubane that neighbors the protonated sulfide. So with that in mind, just looking forward really quick, we've really, E0 and E1 have been really well studied, but there's tons left to do on the cycle of nitrogenase, including how it interacts, more studies on how it interacts with other substrates like carbon monoxide and carbon dioxide, as well as better characterization of E2, E3, and the states that I'm not showing over here, E5 through E8. So with that, I'd like to thank Serena. She's been a wonderful advisor to work with for quite some time here. I also work tightly with Eckert Bill, doing magnetic spectroscopy, and he's been involved in the Mossbauer that took place here. I'd like to thank the De Beer Group and my collaborators on this project within the De Beer Group, all my Beamtime companions, beamline scientists at ESRF and SSRL, and of course my external collaborators who have been instrumental in seeing this project through. All right, I'm up for taking any other questions. I know that's a very short wrap up.
No, but that's good. So Jerry has one that says, what do you see as the next steps in this research program? Oh
yeah, we got a bunch of them. So in this, one of our steps right now is looking at the actual electron transfer step that's occurring more specifically between E0 and E1. So when you have iron protein bound, what happens if you can have iron protein bound in the oxidized state, and if you can trap this in oxidized P cluster state in there? That's an important project we're looking at with rapid freeze quench. We're also trying to use rapid freeze quench to push a little bit further into these more reduced states and get other populations out now that we have a good idea of how to get very precise data. Another project that actually have measurements running right this second in at Spring 8 are looking at effectively what we believe to be the E4 nitrogen bound state. And so NRVS is a really good tool for us here for trying to figure out what the nature of nitrogen binding is once it is actually bound. So we'll see how those results come out. They're getting email data every couple hours. So those are some of the things that we're really closely looking at. I'm also interested in doing some valence to core for hydride states, the E4-4H. Calculations show the changes are pretty small, so we'll see if anybody gives us time.
Just before I call Julia, does this experiment you did, and even this that you talk about hydride, would benefit from the deuterium experiments? Would you be able to see something a bit more clear from having a deuterium there instead of hydrogen?
Yes, well, for those we're doing, or you're talking about for the valence to core, I'm not sure. I could run calculations and see how big an impact that makes. For the NRVS, of course, looking at hydride, we ran some experiments trying to find hydride modes here, and the intensity and the relative energy is just, it's a very, very low chance of getting it. I invite anybody who wants to also try it to do so. It's not an easy experiment, and you might be able to get it if you had a full week for one sample at a place like DL19 OXU, Spring 8. But yeah, it's a very tough experiment. Of course, for anything like this, we do both deuterium labeled and yeah, not labeled. But for the valence core, I'm not sure. It would be worth looking into some calculations and checking it out.
Yuli, you want to ask your questions, or should I ask?
Yeah, there were two questions from me. So basically, are there any time-resolved X-ray diffraction attempts to, have a crystal structures of those intermediates? That was the first question. And the second is, how intense is protein preparation? So basically, how hard is to produce, let's say, only nitrogenase sample without those reducing proteins?
So for I guess I'll answer for the XRD efforts. I'm not aware of any efforts that have been made to do time-resolved X-ray diffraction of this. Doug Reese and Oliver Einsler, some of the most prominent nitrogenase X-ray folks, but I'm not aware of anybody trying to do like an XPEL type experiment. The other part of it is, of course, it has to be under turnover, so it's not, and maybe I don't understand the experiment well enough, but you wouldn't be able to necessarily have a stream of crystals because you have to have this iron protein interacting to turn it over. It's to actually have the native wild type system and reduce any substrate or undergo any of this cycle at all, the iron protein itself is 100% necessary. Doesn't matter how strong of a reductant you have, you will not move along this cycle without the iron protein present. It's believed it's believed that it's a conformational change that happens when you have docking of the iron protein, which actually triggers the P cluster to transfer an electron, and then you backfill the P cluster from the iron protein. So it's really this conformational change that triggers the P cluster to transfer iron, and so you would need that accessibility within a crystal to get that done. There have been intermediates of, for example, CO binding, crystallized using regular X-ray diffraction methods, or still a synchrotron, but hooked onto the loop. But again, it's unknown exactly whether that is truly an E1 or E2 state, or whether it's bound CO, goes here, and ends up back here with CO still bound. So that's also another large project going on. Second part, how intense is protein sample preparation? So because in most of these nitrogenases, there's actually just recently one example of expressing nitrogenase in yeast, but for the most part, we don't have, no, it's not yeast, what is it? I forgot the system that they did this in. It's an incredible feat to be able to put this in any other organism because of the level of complexity of the iron sulfur cluster assembly. And so we really have to produce all of this in native organisms. And so we're using Azotobacter vivalandi. And of course, with a native organism, it's much harder to push it to overproduce, and you get a lot lower yields than you would with a host organism. And so I'd say it depends on how big of a batch, maybe from like 10 liters of culture, you can get like 20 to 50 milligrams of protein after about a week of work. So it's a lot of work to get protein here. As far as separation from the iron protein, that's done using size exclusion chromatography. So that part's not particularly difficult itself. So we separate the proteins, separately characterize them, and then add iron protein back to molybdenum nitrogenase where we want to put it under turnover. I don't know if that answers all your questions, Yulia. Jerry
had a question that then I think if he didn't want to be asked, but maybe we bring this in the end. So Yang Ha, as another one says, do you think that iron moco can hold up 4 electrons? Then most will not. Then most, if not all, iron will be 2+ at the E4 state. Any support for the model complexes that do this all reduce cubane?
So I can answer both of those pretty straightforwardly. Number one, for the second part, the iron protein that is used to reduce MOFI, you can reduce to an all ferrous state. So it can be super reduced. It normally functions between 3 iron 2, 1 iron 3, and 2 iron 2, 2 iron 3 redox couple, but you can reduce it to the all ferrous state using, I believe, like titanium citrate, and there's also several other ones you can, the reductants you can use. And that also still functions to transfer electrons, but there's evidence that that's not physiological. That was actually an argument in like the 90s, early 2000s for maybe like 10 years, people going back and forth of whether the super reduced state of iron protein was physiologically relevant. Actually, should put up, we have a recent ChemRev on the spectroscopy of nitrogenases from earlier this year that dives into a lot of all these little arguments and interesting points through the literature. I will say though that there's very, very strong evidence for that you don't actually have a full 4 reducing equivalents. Again, you have a proton with each of these. And so what you actually have happening is supposedly hydride formation. And so there's strong evidence from Endor experiments that this actually has 2 bound hydrides, and that this is nitrogen binding induces reductive elimination of those 2 hydrides. Then effectively you'd have a 2 electron reduced nitrogen species here, but this is not well characterized enough to say that yet. So the assumption is that we have protonation, that you add 1 proton and have 1 reduction, you add another electron, form a hydride, add another electron, who knows, maybe you protonate it, form a second hydride, and here you have 2 hydrides. So this was an important step in the E1 state of seeing whether or not we have a hydride or whether or not we protonate a sulfur, because either could happen on en route to E2, and it's still unknown what happens at E3. So that's something we also are trying to investigate.
I have one that is more like a curiosity. Since now we have a new member of the Jerry family there. I mean, it's very often that people are trying to find inspiration on these natural enzymes to somehow come up with some kind of artificial model. Yeah. But electrochemically, or even the normal process that you do ammonia, you bind first the nitrogen and then you kind of sequentially add the hydrogen. Do you think this is a clear example that basically you either do it like nature and you will go down that path? You cannot really learn from nature to do an artificial, or vice versa. You know what I mean?
I mean, artificial is, yeah, it depends on what kind of artificial system you want to look at. In terms of materials, yeah, that's a very hard buy. It's a very hard buy to say that exactly what you'd find of how the enzyme does it is something that could be directly applied in material development, because it seems that the way the enzyme does it, again, is through hydride storage, through stabilization of otherwise very reactive metal hydrides, and then in this way, binding nitrogen and possibly having an immediate 2 electron reduction at nitrogen just by way of binding, rather than binding and then trying to add in the electrons, as you mentioned. So for model complexes or even doing designer proteins, I think it's still a promising approach. And even in small mono complexes, you could do on a very, very choice few, you can get nitrogen binding and subsequent reduction without necessarily having to go through that hydride. But I think that it's a very interesting key in like thinking about how to effectively get around some of the otherwise inefficiencies or the side products of materials and trying to do this reaction. And the other, I mean, it makes sense on a system that can do this at ambient conditions. I mean, does it at room temperature and under ambient.
No, and I mean, it's
so the hydride, I think, is like, to be able to do that, hydrides are clearly key.
Yeah, no, and I think this is important because, I mean, again, if you think from a purely heterogeneous catalyst, I mean, your concern is somehow how do you make sure that the nitrogen bind and then somehow you are gonna be able to hydrogenate it because you have very good hydrogenation. But in this case, if you would try to mimic, you would need to somehow produce this highly radioactive hydrides and actually keep them stable long enough that the nitrogen can come and react. And of course, paradoxically, this is a completely different process, you know, like the level of stabilization you have to do, it's completely different. With the other one, you want to absorb the hydrogen and keep it there, where this one, you want to have the hydrides and keep it there until the nitrogen comes over. So it's
the classic problem that Norskov has already addressed very heavily. And yes, what do you, in a catalytic reaction, what do you aim to stabilize, and what are the caveats in stabilizing these different components in basically getting stuck or losing efficiency and things like that. So yeah, it's very tough. I think that in the big picture of, to be honest, I think in the big picture of nitrogenase research, some of the most effective things that will come out of it are probably more on the molecular biology side and being able to put these into our genetically modified organisms to fix their own nitrogen, which again, as I mentioned, Haber-Bosch process, you know, we produce about 40% of the nitrogen, of fixed nitrogen on the Earth, and that requires about 1 or 2% of total energy used, which is a massive amount of energy, right? And of that, also about like 50 to 60, at least I think it's around estimated 60% of fertilizer that is spread onto fields is washed off, just into nothing. And not only that, to get the hydrogen to do the Haber-Bosch process, you need to use steam reforming. And steam reforming reduces massive quantities of CO2. So to make ammonia, you have to currently make tons of CO2, use a lot of energy, and you waste 60% of it. Not to mention all the shipping and shipping costs and the cost of building large manufacturing plants. So it's, I think like that is.
No, but I mean, there is also the argument, of course.
The big thing, yeah.
No, but actually we had Norskov here about a month ago, and he emphasized, for example, on the nitrogen, this aspect that you need, even in an heterogeneous type electrocatalyst, you need to control the proton and the electron flow. So it's not just simply like you absorb nitrogen and somehow this is all gonna go crazy. So and this of course comes from the enzyme, the electron and the proton flow, because this is something that it's in a sense you put it as a given on an electrocatalyst. You can just crank out the pH and you will get the electrons from the electrode. But he said if you do that, you're not gonna produce ammonia. You're gonna most likely just drive hydrogen formation. Good. I don't think there is any other questions. So I think we just left to thank you, Casey. It was very, very informative. And even if I'm not an enzyme person, it's always inspiring to see the lengths that the group of Serena goes to study this protein. I think I would have given up many, many years ago. But it's amazing that you guys persevered. And I'm sure at some point this cycle will have a lot of red ticks on it. Thank you very much.
Thank you very much for having me.